Good morning. As promised, we are back with another chapter of interference. So this chapter, the interference effects are mostly falling under the category of diffraction. We'll see it's a little bit of a longer list than that. But there's a diffraction, and then at the end of the chapter we're going to talk about an effect called polarization. You guys are familiar with Polaroid sunglasses, and polarization is a very important property of light. And it's not actually interference. It's a separate, it's kind of an add-on. It wasn't clear where to put polarization, so they added it on at the end of chapter 35. So these are the topics that we're going to be looking at, and let's just go ahead and get started on the chapter. So what we found back in the last chapter, in chapter 34, when we're looking at interference of light, is that when light comes up along the edge of something, that the light begins to spread out around the edge. So what happens is basically when we have a wide sample of light, the light appears to be going in a straight line, but when we take away some of the edge portions of that light, then the light begins to spread a little bit. This is an interesting interference effect here. I think this is supposed to be a perfectly circular disk, and the prediction is if we look behind the disk, all of these locations, the interference effects will cancel out most all of the light, but at a point right at the center, the light will all constructively add together, and that's what that's an image of. These are just some sharp edges around a razor blade, and then this, we're going to have to come back and talk more about this. This is what's called a diffraction pattern. So we'll get a look at that too. All right, let's see. Oh, well, we just jumped right in. So a diffraction has to do with what will the interference look like if we're just looking at light passing through one opening. But that opening is not super narrow. We have to take into account the width of the opening. So if you think of diffraction as, well, in the last chapter we talked about numbers of slits, but now with diffraction we're going to be looking at what is the width of the slit and what effect does that have. And so these are some pictures of some diffraction patterns for some different light of different wavelength. And what we've got is we have what's called a central maximum, and then we have these smaller, much lower intensity regions surrounding it. Almost all the intensity, if you go in and measure the intensity at different locations, like I think it's like 95% of the light is actually going into that central maximum. But those outer regions, it's not like there's nothing there. That's a pretty significant effect. Now, how are these being produced? It's by sending light through one narrow opening. So one narrow opening is creating this diffraction effect. Let's take a look and see. So this is a drawing that kind of represents the intensity patterns that we were just looking at. And what it says is that when we have a single slit, what we can do is we can take the width of that single slit, and what we're going to show is that we end up with some formulas that look very familiar compared with what we saw back in two-slit interference. So back in two-slit interference, we had d sine theta is equal to m lambda, where d was the distance between the two slits. But with diffraction, the d gets replaced with, now I've used a little a here. My tendency is to use little a, but I've noticed that the book is using big D, and so I apologize for that. I think what happened was, I think I've got some places where I'm using little a, other places where they're using big D. I'll try and point that out, just so you guys are aware. Those are two variables representing the same thing. Again, I apologize for that. I should have made sure the variables are consistent throughout. And I tried that, but I didn't get, a couple places I slipped up. So if we look at m values now, 1, 2, 3, 4, etc., what we find with diffraction, when there's just one opening with a width of a, is that there's a central maximum centered around n equals 0, but when I got to the integer values now are zeros. With two slits, the integer values of m were the peaks. But now the integer values of m are all zeros, except for the center one. The m equals 0 is the biggest peak of all, and then that peak drops off to 0 when m is equal to 1. It rises a bit, drops back down to another 0 and another 0. So in terms of the m's and where the peaks are, it's kind of a reversal. With diffraction, the zeros are at the integers, and the peaks are roughly at the half integers. Not exactly. We'll see that that's not quite the case. And just to finish out the formulas for comparison, the intensity as a function of the m value is going to be I naught. Now this is a more complicated formula. Sine squared theta times sine squared of m pi divided by m pi squared. Now again, I got to use radians for the sine functions that are here. So I got to take the m value, multiply that by pi, set my calculator to radians, and then carry out the calculation. Now what we want to do is go in and find out why do the formulas have the form that they do. They're kind of similar to two-slit interference, but as you can see, there's some significant differences. So let's go back and kind of use the same approach. Now here the book is using big D, and so this is the width. I've got a barrier set up, and the width of that one opening is D. So in some sense, it's a single slit compared with a double slit. And so if it's a single slit, this is all I have to work with. So these are all the paths of light that are coming through. Now if I look in a forward direction where theta is equal to 0, all of those paths, when they get to the screen, are going to reinforce each other, and that's why we get that really large intensity peak right at the center. And then as I begin to move away, let's move at a different angle. Let's look away from the center point on the screen. What does the intensity look like over here? And let's say that we've moved all the way so that there is a full extra wavelength in path length between one end of the opening and the other. So in chapter 34, when we looked at two slits, there were discrete differences between where one path was and the other, and there was a d sine theta, and that was the distance between the two possible paths. Well, now I have an infinite number of paths, because what we're considering here is there's a little bit of path here, and there's a little path here, and a little bit of amplitude, little bit of amplitude on this path, little bit of amplitude on this one, this one, this one, this one. So instead of getting an amplitude of A through one of the slits and an amplitude of A through another slit, I'm getting a little bit of amplitude spread all the way across that opening. All right. Now, when the far end of that path compared with the other end differs by an entire wavelength, that is how we are going to define m equals 1. So the m values are going to be defined by looking at extreme edges of that opening. And so what happens here is now I have all this stuff filled in. So if I have this extreme one here and the one over here at this edge, well, they're in phase with each other, but there's a path right down the middle that differs by a half wavelength, and that's out of phase with the edges. And what I can do is I can go through and say, you know, those are a half cycle out of phase. They'll cancel out. Those are a half cycle out of phase. Those are a half cycle. So I can pair up these paths and show that I'll get complete cancellation. So if all I took were these two paths, like we did back with two-slit interference, those two paths are in phase with each other, that gives me a peak. But if I now break open that barrier and include all the intermediate paths, now I get a 0 because I'm going to get complete destructive interference. Now, let's see, that was a full wavelength. What happens when I get to 3/2 of a wavelength? That puts me pretty close to being bright again. And then when I get to 2 full wavelengths, well, I'm back to where I have complete destructive interference. Okay, so here's an example we can start with. It says that we have a single slit, diffraction, and we're looking at that central maximum. And as we were just talking about, the central maximum runs from n equals 1, where the intensity drops to 0, and then n equals 1 on the other side, where, again, the intensity has dropped to 0. And then right in the middle, the intensity is its largest value. Now, they're saying that the screen here is 20 centimeters from the slit. Okay, here is all the light coming in. Most of this is getting blocked. The diffraction effect is happening just from that small portion of light that gets through. And what they want us to go in and calculate is how wide is the central maximum. So they want us to come in and solve for the angles. What's the angle, the angular size of the central maximum, and then how many centimeters? Oh, it's back to x. It was x to start with, and then it went to y, and now it's back to x. I prefer x. I'm glad it's back. Welcome back, x. So here's the setup. So I got n equals 0, n equals 1, n equals 1, and that's because it's single slit, finite width of the slit. Oh look, I used capital D, so I got this right. This matches the book. So there's a theta here, there's a theta here. This is 20 centimeters. Everything's looking pretty familiar. Now what we want to go back and remind ourselves is the tangent of theta is x divided by L, where x is measured from n equals 0 outwards, and L is the distance across. These are right triangles. Tangents are opposite over adjacent, so x over L. So I can, we got to get some angles here first. Let's see, I'm going to use the formula d sine theta. This is the formula that I had written on that earlier slide. D sine theta, but I wrote it with a little a instead. D sine theta equals m lambda. So that's going to let me go in, and for a value of n equals 1, where the interference pattern zeroes out, I can solve for theta. And the theta value that I ended up with, putting in all the numbers that were given, what was the wavelength of light? The wavelength of light is 750 nanometers. The opening width is given as, oh look at that, 1 micron. Ooh, that is so narrow. That width is so narrow, I can't see it. It's only 1,000 nanometers in size. That's a really narrow opening. Yeah, if we looked at that, we wouldn't be able to see something that's 1 micron in size. So anyway, the wavelength 750, the slit is 1,000 nanometers, and when we look for where is n is equal to 1, that shows up at 48.6 degrees. That's a pretty wide central maximum, and that gives us an x value of 22.7. All right. Now this is a good point. This is a good time to point out that the book introduces small angle approximations. Don't use those, because a lot of the examples that we look at, the angles aren't small, and you guys are you're just starting out. You're just starting out learning how to set these things up. And what the small angle approximation does is it takes this equation, which is the tangent of theta, and that equation, which is the sine of theta, and it says if the angle is small enough, if it's like less than 10 degrees, sine theta and tangent of theta are really, really similar. They're close enough that we can almost set them equal, and so they combine those two formulas. There's a couple of downsides to this. The first downside is you don't really get a chance to learn the individual equations. This is really a two-step process. So this formula specifically gives us the angle, and that's a separate conceptual thing than finding out where the x value is going to be. So this formula is just saying once we know the angle, we can solve for the distance along the screen. Now that's the first reason not to do it, is because you guys are starting out and you want to be able to see in your formulas everything that's happening. And when you use the small angle approximation, you lose information about the angles. And you want to practice seeing that. That's part of the learning process. The other reason that you don't want to use the small angle approximation is because the angles aren't always small and you'll be wrong. Okay, so the answers you come up with are just going to be wrong. And I have to tell you right now, if you're using the small angle approximation just because the book gave it to you and you're assuming that the angles are always small, I'm not very sympathetic in grading. Okay, so please just break this down into 2 steps. When you're talking yourself through, say this is how the angle is related to the wavelength and the slit opening, and then move on and say, and now that I know the angle, now I can relate the distance to the screen with how far off center this will show up. I think it's just really important not to put too many steps together when you're learning things. Make sure that those remain distinct steps so you can understand how the different ideas come together. Okay, all right, enough said. Now this is an interesting conceptual question. Let's take a look at this opening. Now what we're used to seeing are these really thin, narrow openings, and the diffraction happens along the narrow opening. This one is actually fairly narrow in this direction, but it's pretty broad here. So that raises the question, what does happen if I make the opening more narrow? So if I make this opening more narrow, do the angles get smaller or do they get bigger? And by angles, I mean, does the interference pattern spread out or does it get narrower as I make these smaller? Now if we go back to the beginnings of chapter 34 when we first looked at this, what we showed was as these openings get smaller and smaller, the path of the light spreads out more and more. It's kind of counterintuitive. If I'm trying to cause the light to go through a narrower and narrower opening, I will fail. Okay, if I do that, because as I try and get the light to go through something narrower and narrower, it just spreads out more. So, and in the limit, as we make it super narrow, in the limit where we make it no width at all, it spreads out uniformly in all directions. Okay, it's kind of like raising kids, right? So if you put more boundaries on them, they spread out more. I don't know, maybe that's true, maybe not. Anyway, if that's a useful way to remember this, go ahead and use that. So what's going to happen here is this. If we send light through an opening that looks like this, we're going to get more spreading vertically. We're going to get the light spreading up and down on the screen quite a bit, but in the horizontal direction we won't get as much spreading because it's wider. And what they're saying is if we have a loudspeaker at a stadium, where do you want the sound to go? I don't think they do this right. We got to go back and look at loudspeakers at stadiums, because with diffraction what should happen, if I have a loudspeaker that's oriented like this, it should be that the wide region, I don't know if it's a diffraction effect. I think it's something else. I got to think about this. High and narrow. Because at the stadium, what we would want is the sound to spread out to the people in the stands. We're not interested in having it go up and down so the players on the field can hear it. We just want it to go from side to side so it spreads around the whole stadium. And if it's a diffraction effect, what we would want to do is make it narrow vertically so that it spreads out more, right? So in the, maybe I'm getting the vertical and horizontal, maybe that's confusing, but if we make the opening more narrow horizontally, if we make this more narrow, then we should get more spread horizontally. So this, I would say, is not the way you would want to get the sound out to all the fans if it's a diffraction effect that's taking place. All right. And it has to do with, I'm trying to think of what the wavelengths of the sound would be. Man, that's an interesting question. Pay attention at the stadium next time we are there, and we'll think about how that's going to work. Okay. We're going to try and show where some of these formulas come from. I'm not sure this is a good idea, but let's do it anyway. So here is the width of the opening. And as we said, instead of having an amplitude along this path and an amplitude here, what we have instead is we have a bunch of little d amplitudes, all just a little bit out of phase with their neighbors. So there's kind of a continuously varying amplitude effect that is going on. All right. So the extra distance that we have here is going to be big D sine theta, just like before it was little d sine theta. And what we're going to do is we're going to set that equal to some number of wavelengths, just like we did before. Number of wavelengths difference between the two paths. An infinite number of infinitesimal widths. So, right, so we're adding, and they're varying continuously. Okay, so that type of interference goes by the name of diffraction. Now, again, the textbook, this always surprises me. When it's two slits, they call it interference. When it's one slit, they call it diffraction. They're both interference. So we can either have diffraction effect within interference or the two-slit effect of interference. They're both interference. Now what happens is if I imagine a whole series of these little tiny pieces, they're calling them delta E, I'm thinking of it as dA, little infinitesimal pieces. If I'm looking straight ahead, everybody lines up, and that gives me the largest amplitude, and that gives me the largest intensity. But when I start to look a little bit away from that center location, then they don't quite end up in phase with their neighbors. Every path, when I look from one path to the next, let's take a look at the picture here. Ooh, a better picture. There we go. So if I look at all the paths, let's use this as a reference. Now this path is a little longer, it's going to be a little bit out of phase. This path is a little more longer, it's going to be a little more out of phase. This is even a little more out of phase, and then this and this and this. So if the amplitudes are spread uniformly, if we're illuminating the slit uniformly across, then we can say that each amplitude associated with each one of those little, each one of the paths is going to be uniform in size, and if they're all shifted by an equal amount, that will give us a circular pattern. A circular pattern on our phasor diagram. So there's nothing physically on the screen that's circular. It's that taking all of the amplitudes and all of their relative phases into account, that gives us a circular path. Now if we make that assumption for the light going through a single slit, that's enough information that we can go in and predict what the interference intensity formula will look like. So in this case we're going to get maximum total amplitude. In this case the amplitude, now they're calling it E sub theta. So E sub 0 is what's the overall amplitude right at the center, and this is the overall amplitude when we look away from the center by an angle theta. And what we can show is that the combined phase shift is equal to n times the phase shift between neighbors, and what that produces for us is this. If I look at the phase shift between the first path and then the other path at the other end of the slit, so we've got the one slit, I look at the path at one edge of the slit, I look at the path at the other edge of the slit, that would be this represented by this phasor and this phasor, and I look to see what angle there is between them. And this is the angle that we're coming up with. Now, if I look to see what the M value is, if I look at this combination between the first path and the last path, everybody's in phase, that's n equals 0. But if I look at this one and the last one, and what I find out is that this one, in terms of phase, is 1/6 of a cycle shifted. So they just kind of randomly picked this value of 1/6, or I did. So that's 1/6 of a, I mean, I added the numbers in here. So this would be m is equal to 1/6 because this is 1/6 of the way rotated. Now, if I take this full length of dAs and I keep wrapping it tighter and tighter, by the time I get out to n equals 1, the first path and the last path line right up, because there's all possible phases within each of those paths, each of the intermediate paths, and that gives us 0. That gives us 0 net amplitude. Now, if I do 3/2, if I wrap this thing even tighter so that I go through 3/2 of a cycle, then I'm going to get a maximum, or something close to a maximum there. So the intensity depends on the amplitude squared. That's something we looked at in chapter 34. And so as this E sub theta gets smaller and smaller, so here it is a little smaller, there it's gone to 0. Here it's back, but it's not very big. That squared gives us the intensity. Now, notice with the diffraction patterns, another feature of this is, notice how the diffraction patterns never come anywhere near the maximum intensity. And as you get farther and farther out, those fringes that are listed, they just get smaller and smaller. And so, and I guess if we go, yeah, there it is, all the way back, see how the fringes just get consistently dimmer and dimmer as we go out. There's no place where somehow the interference effect creates a fringe that's brighter than the one before it. And that's what's going to happen from looking at this diagram. If I look at how all the interference effects from the individual paths are going to add together, they're always just going to form this phase diagram where the circles get smaller and smaller and more constrained. All right, there's more and more interference taking place. Now here's a diagram where we can actually go in and derive our intensity formula. So what they're calling E sub theta, I'm going to call A total or A net, and then what they're calling E0, the combination, the combined length of all the dAs, I'm going to call A. So this is the combination of all the individual paths, and because of their phase differences, the net effect is that we'll get some cancellation. And so the E naught remains the same, but the E theta gets smaller and smaller. And that's what we've been seeing here, right? Okay, you can see where the E naughts are here. Now what we can do is we can take this diagram, and here's, oh, I went back to using A. Now, that's supposed to be big D. So that's big D sine theta equals m lambda. And what I'm saying here is that the sine, I'm going to take this diagram, the sine of 1/2 beta is equal to 1/2 total divided by r. Now that's a trigonometric function, the sine, and what I'm looking at is this right triangle here. Then what I can do is I can use a circular arc definition. I can say the angle 1/2 beta is equal to the radius here, there's a radius here, times the arc, divided by the arc, the arc length divided by the radius. So this becomes 1/2 A over R. So This is a right triangle formula. It's got a sine function. This is a circular arc, or a section of a circle formula. And it's just written in terms of arc length over r, and that's going to give us something in radians. So this is in radians, that's in radians also. And so what we end up with from the a sine beta equals m lambda, the beta here, the difference in the phase, is going to be m times 2 pi, where m is the number of cycles, and 2 pi is how many radians we have per cycle. Now, how big is the A total compared with A, where A is adding up all the individual paths together? Well, A total over A, according to that formula, the r's will cancel out, the 1/2s will cancel out, and what we're going to end up with is sine of 1/2 beta divided by 1/2 beta. And to get the intensity, we square A total. And so what that, we take something proportional to A total, so it becomes, our intensity formula becomes sine squared m pi over m pi squared. And that's the formula that we've looked at, and we've played around with in some of those diagrams, and now we're deriving it to see how it comes about. All right. Okay. Let's see this. Intensity at the second maximum. So with these interference, with these diffraction patterns, we are having secondary and tertiary. We're having m equals, we're having peaks beyond m equals 1. And so, let's go in and see if we can come up with some of those, calculate some of those numbers. So here is the intensity formula that we just derived. It's going to be based on some peak intensity, which is right at the center. So the peak intensity is right here, and then the whole thing gets multiplied by the sine squared of m pi over, the sine of m pi squared, the squaring comes after, divided by m pi squared. Now in the limit, where m approaches 0, the sine of m pi is roughly given by m pi. You might think that we've got a numerical problem here because as m approaches 0, the numerator goes to 0, but so does the denominator. But if you remember from calculus classes, if you have 0 on top and 0 below, you just have to take a closer look at your functions. And so it turns out that in the limit, as the angles get really small, as m theta gets really, as m pi gets really small, sine theta and m pi theta become essentially the very same number, and that says the intensity at the center, this factor becomes 1, and so the I naught actually is the intensity right at the center. So for that, you can't really use your calculator, you have to use your deep understanding of functions and a little bit of calculus thrown in there in the limit. So this is what the interference patterns look like, and that says that we have this really high peak at m equals 0, and then at the integer values, that function is going to 0. Whenever m hits an integer, the numerator goes to 0, and so the whole thing goes to 0, except, again, the exception here is when m is equal to 0, where everything lines up. So to find out where the function maximizes, what we can do is we can take this representative function, sine of u divided by u, and find out where sine of u over u maximizes. If we think back to calculus, there is a quotient rule that says, what does the quotient rule say? Bottom times derivative of the top minus the top times the derivative of the bottom over the bottom squared. That becomes u cosine u minus sine u times 1 over u squared. It comes to this equation which actually can't be solved directly. It has to be solved by doing approximation techniques. But what we can do is we can take that u, turn it back into m pi. Here is the formula telling us what the m values will be where the peaks are occurring. Now I programmed this into my calculator, or you can go online and program that in and say find all of the values of m that satisfy this equation. And what I ended up with was 1.430, 2.459, 3.471, 4.477. Now, what we're noticing is that the peaks, they don't quite occur at the half integers. They occur just a little bit before the half integers. The peak here is not at 1.5, it's at 1.43. The peak here is not at 2.5, it's at 2.46. I'm sorry, 2.50, it's at 2.46, and then 3.47 and 4.48. It's getting closer and closer to the half integers, but it's always a little bit short. Now what we can also do, once we have found the m values at each of those peaks, what we can do is say, let's use the formula and find out what the relative intensity is. If we say that the intensity right at the center is I naught, 1.00 times I naught, what's the intensity here? And what's the intensity here? And what's the intensity here? And these are the values. So that first fringe is about 5% the intensity of the central maximum. The next fringe is 1.6%. The third fringe is less than 1%. The fourth fringe is at about 0.5%. So you can see the intensities drop off pretty quickly. But that is, that's telling us about that picture. I don't think I'm going to go right back to the very beginning, but it's going to go back to that very, the very first picture that we started with, right? So we'll go back. How far back could it be? There they are. So if that very center point is our reference, that's 100% of the, that's the peak intensity here. This one's about 5%. This is about 20% brighter right here than it is here. And then what was this? This was down to like 1.5% and less than 1%, 0.5%. So these numbers are predicting, we're going in and we're using quantum mechanics and quantum physics to make a prediction about how the interference effects are going to tell us what the intensity pattern will look like. And it worked pretty well, right? When we set up the experiment like we saw in those pictures, it gives us a pretty good representation. Now here is the book's version of this. Let's see if we can. Okay, so I've used the formulas just a little differently and said that this is, the intensity is like sine squared m pi over m pi. And then what they're doing is their formulas in terms of phase. So they're using beta, which is how much phase. Now what they've done in this formula right here, and they've made a big deal about it, is that now they've gone back and done the double slit. So we have 2 slits now, not 1, and they've included diffraction. So they've included both effects. The 2-slit effect is here, and the diffraction effect is here. Both types of interference are happening together at the same time. Now this is the way they've been representing their amplitudes. If you've been following that version, this works fine. Ours is tweaked a little bit. So I'm going to say this. The 2-slit effect gave us an amplitude that was 2a times the cosine of m pi. Now the diffraction effect gave us an a total that was a sine n pi over n pi. So what I've done here is, oh my gosh, I went back and used little a again. So at this point, I guess it really is either or that you've got to be prepared for. So here are the 2 slits. Center to center for the 2 slits is a distance d. Each slit individually is either a width of little a or big D, depending on which variable gets used. So here are the formulas. Now, up until now, we've been using m for both of these, but I can't use M for both of them anymore because they're actually referring to different effects. And the M value for one won't match the M value of the other. So what we got to do then is pick up a new symbol, and I decided to use I decided to use M and N. So I'm going to keep using the M for the two-slit effect, and I'm going to introduce N for the diffraction effect. And then what we can do to actually quite a good approximation is for the A total, we can take the two-slit effect and just multiply it by the diffraction effect, and that predicts an interference intensity formula that is given by I naught. Here is the diffraction effect, sine squared over n pi squared, and here is the two-slit effect, that's a cosine. Cosine squared m pi. There is the combined formula for both effects. Now, what is it we're looking at? Well, if it were a purely diffraction effect, then the intensity pattern on the screen would look like that. Now, how would I get that effect? I just have one slit. So if I have just one slit with some sort of a thickness to it, which here I'm using little a. Boy, it really does go back and forth. So here I'm using little a. Then I would have this pattern. If I had two slits separated by distance d, but the thicknesses were truly infinitesimal, the widths really were shrunk down to basically nothing, then on a circular screen, I would have this. So this is my pure cosine squared factor. This is my sine squared over m pi squared factor. Now, in reality cases, in realistic cases, we're going to have both effects happening together. So I can multiply these two factors, and what that means is I will get a two-slit interference pattern inside what we call a diffraction envelope. So this becomes a diffraction envelope on the intensity because, hey, if this is the limiting effect of diffraction, I'm not going to have any intensities that go above that factor. So let's see, where are the, let me go back and look at the formulas. This diffraction factor, sine, well, let's come down to this final version. This factor of sine squared m pi over n pi squared, that has a peak value of 1 and it goes as low as 0. So that factor is something between 0 and 1. The cosine squared factor also can go as high as 1 and as low as 0. So what that says is when I multiply these together, the diffraction formula, the two-slit effect can't rise higher than the diffraction formula itself. Now what we can also do here on this graph is we can count the interference peaks. So what we can see is by the time, see that place right there on diffraction? That is n equals 1. And if I come down here to n equals 1, what I'm seeing is that happens at m is equal to 0, 1, 2, 3, 4, 5, ooh, this is easier, 6. Now that's a bit of an approximation, but it looks like the m value of 6 lines up with the n value of 1, and that would say that, yeah, so m is equal to 6 when n is equal to 1, and from the formulas that we've worked with, m over n has to equal d over a. So that tells us how wide the slits are compared with the distances between them. So that's kind of an interesting effect. Oh, and here it is, perfect. So we're back to that perfect picture that we started, I think we saw this back in chapter 34, right? And now we're prepared to answer what's going on. So what's happening here is these are the two slit effects, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, maybe 12 is the most missing. And then in the other direction, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I don't think I quite got the center one. It looks like it's something like maybe 12. When m is equal to 12, n is equal to 1. So the lowering of the intensity here is the two-slit effect within the diffraction envelope. Okay, that's what it looks like. All right, so here we go. Here is the pattern. Now, what we're going to do is we're going to include in this example diffraction and the two-slit interference effects. We're going to include both interference effects. Show why the central diffraction peak shown, plotted for the, oh, it is a factor of 6, is what they're saying here. And so the distance between the slits is 6 times the width of the slit, and the way that's being determined is when n equals 1 for the diffraction envelope, m is equal to 1, 2, 3, 4, 5, 6. And the m equals 6 two-slit interference peak is being suppressed by the diffraction envelope. So the diffraction envelope has basically done away with m equals 6 two-slit peak. Okay, so that's what we're looking at. And I get, this is just my own drawing, trying to go in and show where everything is coming from. This is the formula that we've worked from. This is the two-slit effect. This is the diffraction effect. They're multiplied together. Back in chapter 34, we derived little d sine theta equals m pi for the two-slit effect. In this chapter, 35, we've done big D sine theta equals n pi. We're going to divide those two equations. The sine thetas will cancel out, and it says if I'm looking at the same location on the screen, at that location, n divided by m will equal d divided by big D divided by d. Now, when I looked at the screen, when we looked at it together here, when n is equal to 1, m is equal to 6, and that says that it would have to be that everywhere on the screen, whatever the n value is, the m value will be multiplied by 6 from that value. So those values maintain that formula all the way across the screen. And that tells us how to combine the two interference effects together. All right. Limits of resolution. So let's take a look and ask ourselves, when light comes in through kind of a narrow opening, what happens when the light spreads out? And this is called a limit of resolution. Right now it's saying the aperture is circular, but we want to look at both circular and slit cases. Now if I have an opening that is circular, so instead of a slit, I have a small circular opening, then the pattern, the diffraction pattern that we end up with, looks circular in nature, makes sense. So it goes through a thin circle and then it spreads out, but because the opening, which is called the aperture, because the aperture is a circle, it's symmetric, the intensity pattern will also be symmetric. So what will happen is, if this is m equals 1, I guess I'm going to go back and call these m's, then this is m equals 1, and the central peak is circular. So what we're going to see on the screen is a circular intensity peak, and then there's a 0 surrounding it where the intensity goes to 0, and then the fringe, the first fringe is inside here, and the first fringe is going to occur, well, let's talk about m values here, I guess. So this is the first 0, the next 0, and the next 0. Now I may have said n equals 1, I have to retract that statement, because with circular circular apertures, the calculations are going to be more complicated. If you guys want to take a look at this in office hours or something, let me know. Stop by office hours and we can look at it. But more likely, stop by office hours and let's get the basics understood and in place. But you can actually derive these numbers. So it turns out that the zero, that circular zero region, actually occurs at not lambda over d, but 1.22 lambda over d, where the 1.22 comes from carrying out an integration over all of the phase differences of all the light reaching that two-dimensional surface. So it's a bit of calculation to go through, but it does give you that 1.22 number. Anyway, so what's going to happen is we'll have a circular central peak. 90–95% of the light is going to end up here, but then we're going to end up with some light here, and some light here, and some light in the surrounding fringes. Oh, there we do. I was just going to say, I wish we had a picture of this, and it came true. My wish came true. So here is that central maximum, and you can see, yeah, like 90–95% of the energy is going, the light, of the energy carried by the light, is going into that region. And then it's surrounded by a first fringe and a second fringe and a third fringe. So what it says is whenever light passes through a circular aperture, that's what's going to happen. What's going to happen with the light is it's not all going to land straight ahead. You're going to have these fringes of confusion that happen. Now, when does light pass through a circular aperture? Well, like when light enters your eye. Now, the opening on your pupil is pretty large compared with the intensity, compared with the wavelength of light. But still, we can go in and calculate how much of an effect is that. What's the limit of resolution? So let's see what, I think this is probably a good place to take a break. Let's see, I think we're far enough along that we can do that. So let's go ahead, yeah, let's take a break right here, and we'll come back and talk more. Any questions at all, stop by office hours. Let's take a look at what questions you guys have.